Good morning. This is Akor Rashid, Dr. Akor Rashid, your professor in soil mechanics. I'm glad to start a new lecture class for this special situation. And today we are going uh, to talk about soil mechanics chapter 4. Which is about permeability and seepage. Before we start, I want us to make sure is it everything is good, the video and the sharing screen and the audio. No answer, just
I've been here.
okay. So, as we mentioned before, and this is can be kind of review. In this chapter, we are going to talk about the permeability. And the permeability, the word permeability and the seepage are two main important things for soil mechanics, especially for the hydraulic structures, and to measure the quantity or the flow of the water and the behind through the soil itself, and to see how much is the permeable water to check or to guide the safety maybe of the structures, especially those hydraulic ones that I talked about. Before that, we want to just highlight some important things like why we have permeability. Actually, we have already mentioned some of those, so I will quickly get kind of review of what we have mentioned before. So, as you know, here the word permeability was this is a permeability is a kind of physical properties of properties of soil. So let me say as a kind of revision for the properties of the soil that we have earlier talked about. Every, let's say, this is a physical properties of soil that we mentioned that before. We have many different properties of the soil, like what? Like specific gravity, like uh, density, density, and we have bulk, and we have dry density. Also, we have for the physical properties. Also, we mentioned that there is a porosity, and there is what else? What was the porosity and notation letter? It was N. Do you remember this? N was denoted as a letter for and density, which is raw bulk, and raw dry, and also specific weight. And what was the specific weight? It was gamma. Also, we have gamma bulk and gamma dry. And the gamma already is equal to what? It's equal to rho times G. Rho is the density. Also, we have other physical properties. If you remember, the other ones was void ratio. You remember it was, and also based on the physical properties, we have the size distribution. The size distribution of the soil materials itself. We say that we have in soil, we have sand, gravel, and clay and silt, right? So we have said there is a sieve analysis test and high sieve analysis, and the other one was called hydrometer analysis. Will be used hydrometer meter will be used for classifying the soil based on their size, particle size distribution. So for this one, we said there is an effective size. There is which is D10. We have UC, which is the uniformity coefficient, which is D10, D60 over D10, D60. We have the D60 over D10, and we have other sorting materials, which was consolidation coefficient, and we have those are the other the sieve analysis, and also for hydrometers that they will be used only for clay and silt. Remember that we said for soil, those silt and clay soils, usually their particle size will be less than 0.075 millimeter, which is 75 micrometer, which is actually sieve number 200, right? So what pass through sieve number 200 passing, it is called silt and clay. What remain on the sieve number 200, it's called sand and gravel. Those are all physical properties, and we remember that all these are physical properties. We use it to classify soil. Actually, for sieve analysis and hydrometer, we use three methods actually for classifying soil. And we say there is a unified soil classification systems. We have AASHTO, we have UN, United States and Department of Agriculture. Those are the main, and AASHTO. Those are the main methods. We have already took those materials in the previous chapters and how to classify soil. Now, back to our class and our chapters. Today we are taking another properties, which was about permeability. And we mentioned there is the properties of the soil. Let's say permeability is actually, this term is another properties of the soil. So it means that it's like an ID of the soil. The soil can be moved from a point, water in soil can be moved from a part like this, from this is a water table, and this is a point A, and this is point B. So usually this is the ground, this is the soil itself. So we may have the motion or this movement of the water from this part to this part by the effect of two things, by the effect of soil permeability. Permeability, as I mentioned, there is a movement or the flow through porous media of soil. Like if I have, for example, if I have for example, if this is was a situation, if it is like this is the soil particles, maybe clay, maybe gravel, and I have poured water inside over this one. So if this is point A and this is point B, so the movement of the soil, of the water through this the media, that movement, it's called permeability. Permeability, usually it is denoted by K, letter K, which is usually is a coefficient of permeability, coefficient of permeability, and it is usually measured by the same units of velocity, like meter per second, centimeter per second. But the meter per second is not, let's say, it's not, it's very high. Usually we have centimeter per second or millimeter per second. And based on these values, so the soil that have more spaces, more porous on it, there will be the flow of the soil inside it. The flow of water inside this soil will be high enough. So it means that so it is high value of K, which is the permeability, means high value of velocity. So low value or non-permeable soil means there is zero movement, zero velocity of the water. So based on that, and as you remember, and there is in chapter of the permeability, there is like this was the properties. We have mentioned here, here's the movement of soil permeability. Those figures give you, this is low porosity, and those are the low porosity. Means low porosity give you low permeability. High porosity give you high velocity, and high velocity means high permeability. And look at these two figures for loose soil, which is and dense soils. There is how permeability is there. The dense one means it is compacted soil. Dense, it means compacted. Whenever you have to reduce or to minimize the permeability, you have to compact the soil. Like you have to bring compactor and make it the compaction and lower the value of the permeability or the possibility of the movement of the water through the soil itself. Now, this is and there is a rough values of, let's say, of the permeability K. And I think there is a table, let me show you. Here's yeah. That's the coefficient of permeability, as I mentioned, K. You can see for gravel, the flow or the velocity of the water to the soil is between, maybe it reach 100 centimeters second. Means you have in a second, then in 1 second you can have the water go from a point to a point by it is the velocity by 100 centimeters per second if I have point A and B. While for the salty clay or for the clay, there will be the movements very little. Means it needs a time even to pass 1 millimeter or 1 second. It needs about 0.0001. That's so the velocity, it means the velocity, which is the distance over the time, very little. So there will be very little distance, which is the L over the time, very little value. That means we have a very little velocity or very little permeability. And I mentioned that for clay, usually we have, for clay, we have a very little value. And here's the approximate value. So maybe 0.1 or 1 per million, one centimeters per million centimeters may be passed through a second. Okay, and I remember that we took those the method that we can measure this hydrometer or this permeability or conductivity. By the way, it can be called as a conductivity. Usually we can measure, this is a properties, okay, a properties of, of movement. So usually it is should be corrected for a specific temperature. Means you have to make it standard permeability. Standard permeability measurement, it will be the permeability of the movement of water, which water, or water that is in 20 degrees Celsius. Maybe you have, for example, for cold weather countries, as their soil, it will be very, the water in the soil, it is very cold. Maybe they reach 2 degrees Celsius or -2. So we have to take the soil to bring the soil to the lab and use the water, which water? The water in 20 degrees Celsius temperature, and that will be used for to find the properties, the conductivity or the permeability of the soil, and make it as this is called the standard permeability. And how to do that? We will measure the permeability and correct it. This is the viscosity of the water at the degree that have been be measured this permeability through it, and divided by the permeability or the viscosity of water at 20 degrees Celsius. So usually K at 20 will be the K that I'm measuring in the lab times the viscosity at T divided by the viscosity at 20 degrees Celsius. And this can be found through the properties, physical properties of the soil or water tape. Now, this is also a kind of description of the soil itself based on their conductivity values or permeability values. Now, I remember that we have two methods. I told you there is a two method for measuring conductivity. The one is called constant head method, means that you will stabilize or make a water till this one, and this is for inlet. Water is going from the tap, and there will be the movement of the water to this. This is called cell. We have already put a sample of the soil here, specimen, and then there will be collecting of water, collecting of the moved water to the soil here. And basically we will measure the volume of the water that is passed through the soil, and it will go here, and the time. So we need measure volume, time, and then based on the having the equations, we can measure. This is the cell. This is the cell that I'm usually putting the soil here, and here's the distance, the L, that is the specimen or the length of the soil, the passing through it, and here's the equation of falling head or the constant head measurement. Here's the constant head. Yeah, that's absolutely falling. The first one, constant head. Here's the constant head. We will measure the volume, how much volume of water constant. This is a constant level, constant head, and L is the soil that we have using. I'm using the soil, or how I want to, how much the permeability of the soil is that. So the depth or the length of the specimen. Also, I have this, and H is how much is the pressure of water on the soil is that. A is the area of the soil specimen. Usually it's circular, so the area is that, and T is the time for collecting that much on. And basically, you will calculate the permeability. If you check the units, the volume will be in, for example, centimeter cube, length in centimeter, H in centimeter again. A is centimeter square. T is in seconds. So we can say volume centimeter cube with the area, and this is a centimeter squared, and so that will go cancel out. So what's left? L over T, or centimeter per second, or millimeter per second. That's the unit of velocity or the unit of permeability. So based on this permeability, this is the method that is using for permeability. It's called constant head test. The other one is a variable head method, falling head or variable head. This is can be used also to measure the conductivity. Basically, the procedure is that I have this soil, and I know the depth of the soil and the area of the cell of the soil. This is the area, and that's the depth of the soil inside the cell. So basically, we have a small tube. This is a tube of water, and here, this is the drainage of water. So we will put water here, and I will start measuring the time until the water is going from 0.1, for example, to 0.2. So these 2 points, I will measure them, and I will see how much is the value of the. So I have to measure the H1 at time equal to 0 and the H2 at time equal to 0. So delta H is the difference of the movement of the water through the small pipe, and that's called the head. And there is I said, some capital A and small a. Small a is the area of this tube of water, and the A is the area of this cell of water, of soil. Now what left? How to calculate the permeability. Permeability in this one, it will be like this calculation. Is the, permeability can be said, this is the A, which I said this is a small area of this pipe, and L is the length of the soil here, soil specimen, and A is the area of this specimen of the soil, and T is the time that is used to have the point to measure how much is the time that the movement of the soil in the movement of water inside the soil have been used. So to get from point to another point, point 1 to point 2, that's the T. And H1 and H2, as I mentioned, this is the difference in between the start and the end of the head of the water from the beginning to the end. And as you can see, the units here, it's also, let me check. This is the H and the S, their units will be cancelled out. The A is in centimeter square, L is in centimeter, that becomes centimeter cube, that's centimeter square. This is will be cancelled out. So what's left? It's centimeter per time, which is centimeter per T. That's the unit of permeability. And remember this K, we have to measure the temperature of the water that is used to measure permeability. And let's say that will be K at T. So to find the K standard K, which is the permeability at 20 degree, we may have correction of that T by multiplying by velocity of water at T by divided by velocity at 20 degrees Celsius of the water. So, and I want to tell you this was a kind of revision for the previous notion of previous lectures we have in campus for the soil. Now, I think you remember right now what we have took in the previous lecture, right? And these are the examples we have done in the class based on how to find those values of permeability in the whether we are using falling head or constant head method. Now, today I'm going to talk about if what we have here. This is a different sorry. Different soil layers that we have. If I have a kind of soil layer here, now usually we in the reality we have soil with different layers. Like this is a soil. This is another soil. Means what another soil with other structures, with other specific size, with other gamma, with other. So they have both different in size or in properties. So what we have here, there are soil 1, let's say, soil 1, soil 2, soil 3, and layer 3, and so on. And usually, though, this is in the nature. Now, when we have water direction of the seepage or the water that going from a point to a point, it will be like this. Now, we have the L. Here's the L, right? The distance that is the water is going from this side to this side. Now, tell me, by the way, we have to know the depth of each layer. That's called H1, H2, H3. Now, can you tell me overall, how much is the value of the K for all those layers? We mentioned that this is a movement of water through this layer, right? So it will be used for this soil. We have a property which is K, K1. This is another soil, so it means that we have K21, and this is another soil that K3 and K4. And if we are talking about horizontal flow, we have to mention the K as KH, horizontally permeability coefficient. Means, sorry, it means how much centimeter horizontally will be used or will be passed through the water through or the journey of the water through the soil horizontally, how much centimeter can be through a specific time. That's horizontally. If you are talking about vertically, it means you have to mention this soil has a properties which is K, but it is vertical permeability, not horizontal. So for each layer, we have two things. K, vertical, means the flow is going this way. Or we have K, horizontal, which means going. And by the way, this is called two-dimension. Two-dimension permeability. It means in XY. But if you have multi-layer like this one and this one and this one, so overall, if I want to see how much is the total vertical permeability of the whole layers, it have to be found. How to find? It to have be found through those values, and we have to use the following equations for vertically, like what we have in the lectures. So you can see here's the horizontally average, let's say total permeability of the soil. So to find the horizontal equivalent, it's called equivalent K equivalent, it means for whole layers. And while I'm talking about horizontal, so we have to mention this is the horizontal permeability equivalent for the whole list. Means I am talking on this whole soil portion as a one unit. And I want to see how much is the equivalent value of the permeability. As you know, we have horizontally for soil 1, soil 2, soil 3, and soil n. So the equation is like this. Constant head, equivalent permeability in horizontal direction is equal to what? Summation of each one, permeability of each layer times its depth, its I. So I will multiply this by this value plus this by this value and plus this by this value and so on, and add them together to get a summation, and I will divide all of them by the total depth of the soil. So total depth is H. This H is the total, H1 plus H2 and so on, H3. So for horizontally equivalent, it had been, so you have to multiply each layer's permeability by its depth, each layer's depth by its depth, and so on, and then divide them by the total depth. That will give you an equivalent permeability for the whole soil layer. In terms of very horizontal one, in terms of vertical permeability, those vertical ones, I wanna see. Tell you. Let me. Yeah. Those are the verticals one. For the vertical equivalent, K vertical equivalent, we have another equation. That's the equation. So those are the vertical permeability. So K vertical equivalent, usually it is the total depth of the whole layer. This is called like a series connection. It is series. So the water is going from this direction to this direction. So it means it passed by layer 1, layer and layer and layer and layer and layer. So it is in series. The previous one, like it's in parallel. If you remember, it is like what we have in electricity. These are the connection. This is the resistance, and the current is going this way. So this is called a parallel connection, like flow, horizontal flow. And also we have series, which is like this. Number 1, number 2. So the flow is like this. So we have layer 1, layer 2. So that's called vertical. So so back to this one. This is a series connection. So for this one, the K vertical is equal to H over H1 divided by KV1, H2 divided by K2. So it's the answer. This is the right equation. So I can summarize this one by comparing those two ones together. For K horizontal equivalent, the method is summation. For each layer, we have its horizontally conductivity at I times the depth of the layer itself. So I will make it summation for I equal to 1 to n. The n is the number of the layers divided by h. Here its h is equal to h1, h2, till the edge in. This is like we have horizontal flow. It means that this is called parallel flow. For the vertical one, K vertical equivalent, it is the total depth of the whole layers divided by, for each layer we have its own depth divided by K, its own vertical permeability. By the way, the term vertical and horizontal will depend on, can be said, this is the depend on the flow of direction. If we have, it is better to say this is parallel soil layer flow. That's so the flow will be parallel. This is the series soil layer flow. That will be better to you. So for vertical, it means the flow is going series. So H1 over KV1 plus H2 over KV2 and H3 and so on. So this is for series and this is for parallel. Do you have any question till now? Is it all of things are clear?
All clear, doctor.
Clear. Good. So those are the most important things for permeability. And next to this, we have also the Darcy's law. Darcy law, it is a kind of, let's say, it's also the properties to find the properties of soil. This is called gradient. Gradient, flow gradient, or let's say flow gradient means delta H. If I want to show you, when the water is going from this point to this point, in point A, it has a potential head, it has an head. And when it's going to point B, it will lose some head, means delta H. So delta H over the depth that is, or the distance that has passed through these 2 points, that's the L. Yeah. So this is L. So that's called velocity gradient or the hydraulic gradient. Hydraulic gradient, it is a term that is usually used for measuring the flow velocity. We mentioned that this is a K. K is the properties of the soil permeability. While we have, as much as you have high K, means the flow is the flow of water through the soil is very speedily. Lower K means very low. Now, exactly if I want to tell you what is the velocity, is that it is not a matter only of the K. It is a K and it is the head of water and the difference from the point to point. So as much as we have more delta H, means the flow here is the high, the potential high pressure is that in here, and low in the second one, means also a high C. So delta H, if I have high delta H, means also the velocity is high. So Darcy come and combine those two properties, combined by having the delta H and L, and he said there is a V is the approach velocity, the velocity of the water inside the soil can be combined by what? By I, which is the delta H over L, the hydraulic gradient, and the K, which is the permeability of the soil itself. So this is called Darcy's law. And Darcy's law, and if you tell me what K is that, the K will be usually equivalent K. And if I have horizontal, so the V is will be horizontal. If I have K vertical, the V is will be vertical. And so now also Darcy mentioned that this V, the velocity, is through the layer of the soil will be, if I have, this is the soil, specimen, soil, and it has a specific K, and it has a specific I, means there is a L and there is a delta H. So when we have using Darcy is telling that the velocity is equal to K, which is usually measured by centimeter per second, times I, which is unitless. So this velocity is exactly the velocity of water, but before entering the soil. That's called approach. So V is approach velocity. Now, what Darcy mentioned, there is another thing, the velocity inside the soil. The velocity inside the soil, it's called seepage velocity. Seepage velocity. This seepage velocity is related to the approach velocity by what? By usually we say Vs is equal to a portion of V. But what is that portion? That portion, it will be 1 over n. And by using this derivation, usually here's the velocity. The seepage velocity, it means the velocity of water inside the specimen, the flow inside this one, Vs, and V is here. So this Vs is equal to the V divided by the V divided by N. And remember, N is porosity. Porosity, usually porosity value should be less than 1. So usually Vs is greater than V. And this is normal because the water before entering the soils have a velocity which is little, but when it passed through a filter like this, porous media like this, it has to be very speedily more than this because it needs to get out from the soil. So here's the V over N. So the seepage velocity is equal to V over N. And we said N is a value less than 1, means this the denominator of this value is less than 1, so this will be bigger than the velocity. That's the seepage theory, and we have the seepage. Usually, I said this is called Vs. This Vs, like K, it has to be either horizontal or either vertical, and maybe it will be another direction, 3 dimensions. So usually there is another equation or another theory which is called Laplace equation for continuity, means the movement of the water through those the soil of the water inside the soil.